Hello students and welcome back. In this video we'll begin the playlist for Chapter 12, Liquids, Solids, and Intermolecular Forces. This chapter only has one new equation for us, which is the Clausius-Clapeyron equation, which relates vapor pressure to temperature. So we begin by discussing water and perhaps think about it in the space station. If you release water in outer space, well, in an enclosed environment like the space station, then there's no gravity there and water will form a sphere. So you've probably seen videos of this where it floats around in the form of a sphere or like a blob, and you might ask yourself, why does it form this sphere? Well, it forms due to the intermolecular forces of the water. So water exists in three different states. We have solid, liquid, and gas state. Okay, and the gas state is called steam. The solid state is called ice. So we have here some different properties of those three states. We have steam, which exists at 100 degrees C and has a low density of 5.9 times 10 to the minus 4. Liquid water exists at around room temperature and has a density of 0.998 grams per milliliter or cubic centimeter. And solid ice, okay, water is, or in other words, ice is solid water at 0 degrees C, and it has a density of 0.917 grams per cubic centimeter. We see here the molar volume for each of these. And notice that it's much larger for a gas, and that's because the gas particles are much further apart. Okay, liquid and solid water, okay, are much closer together and have a much similar molar volume. So we have 18 milliliters per mole of liquid water and 19.6 milliliters per mole of solid water. So water is unusual in that the solid form actually has a lower density because it takes up more space than the liquid form, and this is due to the crystalline structure that forms in the solid state, okay, because these molecules are pushed a little bit further out in the solid state versus the liquid state. All right, and we could see here that in the gaseous form, steam has a low density, an indefinite shape and volume, and weaker intermolecular interactions than liquid water, which has a higher density, an indefinite shape, but a definite volume and moderate to strong intermolecular interactions, versus a solid water, which has a higher density, a definite shape, definite volume, and stronger intermolecular interactions. So this is true for generally most matter, but we can think of it in terms of water a little more easily. We can go from a solid to a liquid by adding heat or removing heat. We can go from a liquid to a gas by adding heat or removing heat. And we can also do the same thing with pressure. So if you reduce the pressure, you can form a gas, or if you increase the pressure, you can form a liquid. The particles in a liquid are closely packed together, but they have the ability to move around, which makes them incompressible and allows them to take the shape of the container that they're in. Gases are more compressible because there's so much space between the individual particles. So if you get gas, for example, if you get air, for example, in your brake lines in your car, then that will allow that to be compressed and it'll make your brakes feel mushy. So that's why we use liquid brake fluid in brake lines in cars, so that because liquids are incompressible and you won't have mushy brakes as you would if you had gases. All right, and so gases are compressible because there's a lot of empty space between the particles and they can be squeezed closer together by adding pressure. We can visualize that here. Molecules in a liquid are not easily compacted or compressed, but in a gas they are more easily compressed. So we have a couple of different types of solids. We have crystalline solids and amorphous solids. Crystalline solids have a regular ordered structure, and we think of crystals such as table salt as being in that form, or a diamond. And amorphous solids generally don't have long range order. An example of this would be like a plastic. Right? Which state of matter is compressible? This is conceptual connection 12.1, solid, liquid, and gas. Of these, the gas is compressible. Now we can change phases between in different substances by adding temperature, like we talked, adding heat, like we talked about, by increasing the temperature. So solids melt and liquids boil when they're heated, and we can transition between these states by adding heat or removing heat. We can sometimes also transition between these states by increasing or reducing the pressure, which increases the or decreases the volume of a gas. So again, if we add heat, we can convert a solid to a liquid. If we add more heat, we can convert a liquid to a gas. We can convert a gas to a liquid by removing heat, or a liquid to a solid by removing heat. But you can also convert a liquid to a gas by reducing pressure, or a gas to a liquid by increasing the pressure. So for example, when you open a bottle of propane, you aren't doing anything to increase the temperature, but some of the gas will escape, and this will lower the pressure in the tank, causing more gas to escape. So by lowering the pressure, you're actually causing the propane to convert from a liquid to a gas. And you'll actually notice that the outside of that tank will become cold, and that is because evaporation is an endothermic process, and we're going to talk about that later on in this chapter. Here we have a diagram of liquid water. Alright, so which of the diagrams below best depicts the vapor emitted from a pot of boiling water? A, B, or C? So A depicts boiling water because we see that the water hasn't, the molecular bonds in the water have not been broken apart. For B, we have oxygen and hydrogen molecules, and C depicts oxygen and hydrogen atoms.